Asymptotic analysis. When someone says an algorithm is O of n squared, what does that actually mean? It's not about how fast the algorithm runs on your laptop right now, it's about how it scales. And that turns out to be one of the most important questions in all of computer science. Here's why it matters. Imagine you've got two algorithms that solve the same problem. Algorithm A takes 10 times n steps. Algorithm B takes n squared steps. For tiny inputs, they're about the same. And B might even be faster. But watch what happens as n grows. At n equals 10, A does 100 operations, B does 100. They're tied. At 100, A does 1,000, B does 10,000. At 1,000,000, A does 10 million, B does 1,000,000,000. The gap doesn't just widen, it explodes. Asymptotics capture exactly this. Which algorithm wins when the input gets big? And for real-world problems, that's what actually matters. That's what big O is for. It gives you an upper bound on how fast a function grows. When we say f of n is O of n squared, we mean for large enough n, f grows no faster than some constant times n squared. Now here's the beautiful simplification. We drop constants. We drop lower order terms. So 3n squared plus 5n plus 7. That's just O of n squared. Why? Because once n is big enough, the n squared term swamps everything else. The 5n and the 7 become invisible noise. We only care about the dominant term, because that's what actually controls how the function scales. Let me show you how different growth rates compare. O of 1, totally flat. Doesn't grow at all, no matter how big n gets. O of log n. It grows, but so slowly you barely notice. Doubling the input size only adds a constant. O of n, a straight line, proportional to the input. 10 times the data, 10 times the work. And then O of n squared. It takes off like a rocket. At real-world scales, the difference between n log n and n squared can literally be the difference between a program finishing in a second and one finishing in a century. Your turn. You have two nested loops, each running from 0 to n. What's the time complexity? It's C, O of n squared. The outer loop runs n times. For each of those, the inner loop runs n times. Multiply them together and you get n squared total iterations. Asymptotics tell you how algorithms scale, not how fast they are on tiny inputs. Drop the constants, ignore the small stuff, and focus on the dominant growth term. That's the whole game.